Welcome back to Astronomy 405, Physics of the Solar System. Today we're going to be talking about planet surfaces. This lecture is going to divide into 3 parts based on our goals today. So our goals today are first about rocks. How do they form? What are they? How do we tell them apart? How do we classify them? Then the next goal is about volcanoes and tectonic features. And then we're going to talk about erosive features. This lecture will be about rocks. So, our goal is to identify the 4 kinds of rocks and under what conditions they formed. And I've already introduced this idea previously. So, what a rock is the collection of minerals. Remember, a mineral is a substance determined both by its chemical structure and its crystal structure. Because diamond and graphite have the same chemical structure, they're both carbon, but they have different crystalline structures, so they're different minerals. And if you put a bunch of minerals together, you get a rock. Now, we classify rocks based on how they formed. There are the 3 you're familiar with: igneous, metamorphic, sedimentary. But there's another type of rock that planetary scientists have to concern themselves with, which is primitive rocks. Those are not very common on Earth. Their exclusive source is some, but not all, meteorites. So what is a primitive rock? Let's start there because that's the new one. Now, some meteorites, they're old, but they also show very little signs of having changed. So from radioactive dating, which we'll cover later, we know that they formed over 4 billion years ago. But there's been very little sign of any sort of change since then. These meteorites have been floating around the solar system until they enter Earth's atmosphere, make it through, and hit the ground. So not all meteorites are like this, but some are. So we only find primitive rocks as meteorites because they are only part of bodies that are small enough that they don't really undergo major geologic activity. Planets, large moons, dwarf planets, larger asteroids, alter rocks enough that they're going to be one of the 3 other types we talked about. So what defines primitive rocks? We might talk more about meteorites, but they're made of minerals like olivine, pyroxene, iron, nickel. They look a bit like this, and one of their signature characteristics is chondrules. They're small spherical grains embedded in the rock. All right, so let's move on to the kind of rocks that planets make. Igneous rocks are made when you have a liquid rock, magma or lava. It cools to solidify, and now you have an igneous rock. Now, we have 2 basic ways to classify igneous rocks. The first is intrusive versus extrusive. And that's basically a function of grain size. You can see at the top there's an intrusive rock, at the bottom there's an extrusive rock. The intrusive rock is, you can see, has very distinct large grain crystals in it, and the extrusive rock is really fine grained. And the difference is that intrusive rocks, they form underground, so they cool off relatively slowly so crystals can grow pretty big. Extrusive rocks form on the surface, so they cool very quickly, so all the crystals grow at once, so they can only get to be very small. Now, we can also classify it based on the type of the melt that make the rock. Now, this works great for planetary science because if we're classifying intrusive versus extrusive, we need a close-up picture. We need a lander or a rover or a sample return or some other means to look at the rock close up. And if we only have orbiters, that's no good. But orbiters can still get a sense of chemical composition from spectroscopy. Spectroscopy of solid minerals is a bit more difficult than diffuse gas, but it's doable. So a good basic classification would just be felsic is the rocks that have lots of silicon dioxide, silica, and a mafic rock has less than that. Now, still, silicon dioxide is still really common as a mineral in rocky material. So even a mafic rock is only less than half silica. But we could still grade something on that scale. You can see this plot on the right shows not only the silica percentage, but the percentage of alkali oxide, sodium oxide, potassium oxide, to kind of classify rocks. You basically plot a given rock on this plot, and whatever little box it ends up, that's what it is. Now, what we've noticed is that basalt, which is mafic, so it has relatively little silicon, and extrusive, formed on the surface, is really common on the surface of planets. Here's a picture of some lunar basalt brought back from the Apollo missions. There's a picture of Mars basalt on site. And the interesting thing is we found very, very little granite and other felsic rocks off of Earth. That tells us something about the composition of the lava that forms these rocks. And we're going to come back to that when we get to tectonics. So for the Moon and Mars, we have lots of rocks. We've had multiple landers there. For the Moon, we've had sample returns. For Mars, we've had Martian meteorites, which are like sample returns but free, and we don't get to pick where we get the rock from. And it's been sitting in space for thousands of years. So Venus is a little harder. I'm going to keep Venus. We've had a few landers, but they never last very long because Venus has terrible surface conditions. Now, they have lasted long enough to identify that there's lots of basalt on Venus, and that there's some difference in rock composition from the various places that we've landed landers. And we have other reasons to suspect Venus has lots of volcanic rocks. On the other hand, Mars rocks, we can make those kind of classification plots we make for Earth. So this plot shows rocks from Pathfinder, Opportunity, and Spirit, as well as comparing them to what was seen in orbit. That's the testing. And the main point of this plot is to show both that what we see from orbit can be matched to what we see on the ground, which is always useful to know, and to show just the volume of data we have on Mars. Now, Mars is complicated a bit by the fact it is covered in this red dust. TESS or other orbital instruments can't do much about that, but the rovers or a lander can bring along something to clear the dust off. This is a picture of a rock drilled into by one of the rover's rats. That's the rock abrasion tool. It has a little brush and it has a little drill, and it lets them get off the dust to see. This has been color tinted, so a gray rock looks rather blue because it's not red like everything else on Mars. Now let's look at sedimentary rock. That's the next one on the list. Now, what a sedimentary rock is it's a rock made of fragments of other rocks. And one way you can classify that is how big are the fragments. Again, you can't do that from orbit. So a conglomerate has really big fragments like pebbles. Sandstone has sand-sized fragments. They're visible to the unaided eye, but not easily. And shale or mudrock has tiny, tiny fragments. Now, this classification scheme works fine on when you're a lander or a rover. It doesn't work when you're a orbiter. You're just seeing whatever the rock fragments are made of, which isn't always useful because they're going to be made of whatever other kinds of rocks are around. Now, sedimentary rocks tend to require something to move rock around and to break it up and to stick it back together, which usually means an atmosphere or liquid. So the process of sediment, of ground up pieces of rock becoming sedimentary rock is called lithification. Now, some of it is just mechanical, or you take a bunch of sediment, you compress it, and it kind of sticks together. But more usefully, if you have a liquid, the liquid can dissolve things, can dissolve minerals. Then when the liquid evaporates, the minerals recrystallize and form kind of a cement. On Earth, the typical minerals are carbonates, sulfates, and chlorate. So the liquid part depends on having a liquid when the rocks are being formed. Mechanical can happen anywhere. In fact, there's one kind of sedimentary rock that can form practically everywhere, and that's a breccia. Now, the difference between a breccia and a conglomerate is mostly the way the fragments of rock look. Conglomerates, the fragments tend to be eroded. They're very round. Breccia is very angular fragments. There hasn't been much erosion. So here's a picture of a breccia on Earth, and you can see it looks like, you took a rock, smashed it, and then glued it back together. And you can get this on airless bodies because what can glue things together is partially melting the rock. Not entirely, because then you just get an igneous rock, but just enough to take all these solid rock fragments and glue them together into a new rock. So this is a picture of a lunar rock that is an impact breccia. In this case, it's not a one the Apollo astronauts brought back, it's a meteorite. There are rocks brought back from the Apollo missions that have this sign. So we can get breccias as a type of sedimentary rock on an airless body like the moon, but not the other kinds. Now, in Venus, we don't have a liquid to glue it together, again, besides an impact breccia, but we do have plenty of wind to make and move around sediment, and we can do mechanical pressure. Now, that means the rocks will be weaker than igneous rocks, which is what Venera 13 and 14 noticed about some of the rocks, was that they were weak to crushing. And they also showed layers, which tends to be a category of sedimentary rock, that they have these nice layers as sediment is repeatedly deposited. Now, Mars is full of sedimentary rocks. It's got wind, and it might have had past water. And that's one of the reasons we're interested in it, because it has a record of whenever the rock was formed, of what the aquatic conditions were, what the condition with water was. So here's some sandstone from Victoria Crater. We also have some conglomerate and some mudstone. So we've landed on the moon, Mars, Venus, Earth, of course. There's one other place we've landed that might have kind of sedimentary rocks, and I'm using air quotes here, which is Titan. Now, Titan gets tricky because the rocks are actually a mix of water and organic compounds. At the temperatures of Titan, about 90 degrees Kelvin, water is a mineral. Or rather, more properly, ice is a mineral. But we have wind, we have liquid, we can make sedimentary rocks. This picture from the Huygens spacecraft shows rocks that have been eroded to be nice, round river stones. Feels weird to call what Titan has rocks, even though it acts, geologically speaking, it acts a lot like a rock. All right, metamorphic rocks, our final type. Metamorphic rocks are what happen if you have another kind of rock, an igneous, a sedimentary, or another more metamorphic, or a primitive rock, and you put it under high temperature or high pressure. Now, you could just raise the temperature and pressure by burying them, or you can have a volcanic feature, or you can have an impact feature. Interesting impact features we can get. On the right is what's called shocked quartz. Basically, when you have a sudden increase and then decrease of pressure, you create a lot of microscopic fractures in crystals. This is called, when this happens to quartz crystals, silica crystals, which are really common, called shocked quartz. It's often the sign that something really violent happened here, often an impact, but occasionally we find these at nuclear test sites. You also have this characteristic form of rock called shatter cones. So those are particular of interest to planetary science, because we're always interested to find more places where impacts have happened. And on Earth, a lot of the other geologic processes cover impacts up. So finding these mineralogical signs can often point us to a place where we need to be looking for an impact. Okay, so that's about where we're going to leave. So part 2 will be tectonics and volcanism.